Asymptotes, key features on certain graphs. When we're drawing our sketch, curves always bend towards the asymptotes when we're drawing it. We saw that curves will never cut a vertical asymptote, but the horizontal and oblique asymptotes, remember that's telling us what happens out of the extremities, plus or minus infinity. If we do a polynomial division, we can always break it up into something like this: the quotient plus the remainder over the divisor. And when it's in that form, we can get a lot of information. The bottom of the fraction, that's going to find our vertical asymptotes. Bottom of the fraction can't equal 0. The quotient turns out to be the horizontal or the oblique asymptote. And then the remainder, well, we solve remainder equals 0 if it's possible. If it is possible, that'll tell us where it does cut the horizontal or oblique asymptote. If it's not possible to solve it, then it doesn't cut the horizontal or oblique asymptote. Let's use this as an example. I've already factorised it, so it's x plus 3 times x plus 2 over x minus 1, x plus 1. Well, I'll do a polynomial division to see how we can fix this up. So I've expanded it out to make the division a bit easier. So x squared minus 1 into x squared plus x minus 6. So x squared into x squared goes once, and we end up with a remainder of x minus 5. There's our function rewritten: 1 plus x minus 5 over x minus 1, x plus 1. Let's extract all the information to help us draw the graph. So my x-intercepts, I'll go back to the top of the fraction, the original one. We'll make that equal to 0. That'll find x-intercepts. And so we've got negative 3 and positive 2. Plot those in. Okay. The y-intercept, just like any function, sub in 0. And in this case, we get 6. So I've plotted that in. A vertical asymptotes, bottom of the fraction can't equal 0. So we know there's vertical asymptotes at plus or minus 1. Put those in. The horizontal asymptote we have in this case is y equals 1. Draw that in. But then looking at the remainder, x minus 5, it is possible for that to equal 0. So at x equals 5, we know it cuts that horizontal asymptote. Now, I've got to go through all those points. I've got to bend towards the asymptote. That pretty much now gives me enough information to draw the curve. Over on the left-hand side, it must do that sort of hyperbolic shape because it's got to go through minus 3. And then it's going to bend towards these two asymptotes. I probably did the middle bit next now. I know it goes through the point 6 and it's going to bend towards those two asymptotes. So it's going to have a U shape, or it might have one of those inflecting shapes. But I know it does not cut the horizontal asymptote between minus 1 and 1. We found there's only one spot. It's over there at 5. So that means there's only one possibility. It must be that U sort of shape between the two asymptotes. Now we get to the right-hand side, and this is the one that's quite interesting. I've got to go through 2. I've then got to go through that point of intersection of 5, 1. But then I'm going to have to turn and come back down to bend towards the asymptote. Now, if I remember correctly, this is going to look a bit dodgy. There we go. I might have exaggerated it a bit there. But at some point, it's got to come back down, if you get what I mean, and then bend towards the asymptote to do it. So it starts down there, goes through 2, goes through 5, and then eventually it'll turn and come back down. Once we investigate in calculus a bit more, we can find exactly where it does turn and come back down. Let's try another one. X minus 2, x minus 1, x plus 1 over x plus 2, x minus 3. Again, I'll do a polynomial division. X squared and x cubed goes x. Leaves me with a remainder of minus x squared plus 5x plus 2. We can keep going. X squared into minus x squared is negative 1. Minus x squared plus x plus 6. Remainder 4x minus 4. That's where we stop. Remember, once the remainder is of degree that's less than the divisor, that's when we stop. So I've got a linear function. Okay, let's get the information. I now know I can rewrite this function as x minus 1 plus 4x minus 4 over x plus 2, x minus 3. X-intercepts, in this case we have 3 of them. So minus 1, 1 and 2. Y-intercepts, sub in 0, we get minus a third. So I'll put that there. We have vertical asymptotes at negative 2 and positive 3. Draw those in. We have an oblique asymptote in this case at y equals x minus 1. I already know the answer to the next question because look what's happened. My oblique asymptote goes through that x-intercept. So we should find it is possible to solve 4x minus 4 equals 0. And indeed it does give us the answer x equals 1. So we know it cuts it there. We should now be able to draw our diagram. Now on the left-hand side, we have no points on the left of -2. Got to bend towards the asymptotes, but there is no x-intercept on the left-hand side. So it must be trapped in that little triangle down the bottom. So in there. Okay. Wow. I've got to go through all of those points and bend towards the asymptote. My shape is forced because if I was to say start from down the bottom at -infinity and come up to -1, I'd have to cut the oblique asymptote, which I know only happens at +1, so it can't do that. So we must start up at +infinity and come down, go through our points, and we have it. The right-hand side, we have a similar situation to the left-hand side. We've got no more x-intercepts, so it must be trapped in that little triangle up the top there. And so there's our graph. But let's have a look in particular now, reciprocal functions, and they often create asymptotes. 1 on x being the classic example, it's the reciprocal of y equals x. So if we want to draw the reciprocal of a function, again, we can start with the basic curve, whatever function x is. But this is what will end up happening. When the original function is 0, then the reciprocal now must be undefined. We'll end up with 1 over 0. No good. Probably be a vertical asymptote. Might end up being just a point discontinuity, but we know there's going to be a discontinuity there. Here's random curve. I tried to get all sorts of features in there. I've got different turning points, I've got inflection points, I've got a vertical asymptote there, I've got a horizontal asymptote. But what we're saying is our x-intercepts on our new curve will become vertical asymptotes potentially, maybe point discontinuities. We'll see what other information we can draw out. When the original function approaches infinity, so its y value is getting really, really big, if we turn it upside down, it must now approach 0. In other words, the original asymptotes will become x-intercepts. So it's like the reverse of the first point. If the x-intercept became vertical asymptote, then when we turn the vertical asymptote upside down, you get an x-intercept. Sort of. There it is, but you'll notice I put a hollow circle there. It is still undefined at that point. Just turning a function upside down, well, if that x value is not in the domain of the original function, when I turn it upside down, it can't be in the domain of the new function because it wasn't there to go into the new one. So it sort of looks like an x-intercept, but now we do get a point discontinuity there. 1, well, the y value of 1 is good when we're turning a curve upside down because when you turn 1 upside down, you get 1. So that's why it's always good with the graph to know where the y value of 1 is, because I know that the points will stay the same. So at y equals 1 there, wherever the original curve was, the new curve will also be going through those points. But the same thing would happen at -1. Turn -1 upside down. So let's plot that as in. So there's -1. I had this horizontal asymptote, don't know what the value is, but I do know it's less than 1. Well, if I turn a number less than 1 upside down, I must get a number that's bigger than 1. So again, I don't know exactly where it is, but I know it's going to be above 1. So there'll be a horizontal asymptote there. Now, here's an interesting thing. When the original graph is increasing, then when we turn it upside down, the new graph should be decreasing. And vice versa, the other way around. So we can look at the original graph, see where it's increasing, turn upside down, we know the new graph will be decreasing. The sign's not going to change. Turn a positive number upside down, it's still going to be positive. Turn a negative number upside down, it's still going to be negative. So nothing will change there. So let's go back to this graph. What do I know? See all these areas I'm shading in? I know that's where the curve will travel. How did I work it out? Okay, let's start at the left-hand side. The original graph was below the number 1, but above the horizontal asymptote. Therefore, when I turn it upside down, the reverse should happen? It'll be above the number 1 and below the horizontal asymptote. Into the next section. The original graph was completely above 1. So my new graph will be below 1, but it can't change sign, so I know it's got to be contained in that little region there. Now, next one. I know I'm dealing with negative, so it looks strange. I'm actually above, below, say that again. We're below -1, so therefore the new graph will go above -1. And then we go to the next section, below 1, so I've got to be above 1. Above 1, got to be below 1, and so on for all of those regions. So I now know where it travels. Now this uses a bit of calculus, and once we've done that, this will be a little bit more obvious. But this is a way of explaining it. You see, when you differentiate 1 on function x, you end up with this expression here, minus the derivative on the function squared. So stationary points, those turning points. If the original graph had a stationary point, which means the derivative is equal to 0, then the new graph will also have a stationary point, because its derivative will still have 0 on the top there. What do we need to know? All we really need to know is, hey, this turning point, at that x value, there's still going to be a turning point. Its y value is going to change. Its y value was above the horizontal asymptote, so therefore when I turn upside down, it'll go below. But also, more importantly, it's a number bigger than 1. When I turn a number bigger than 1 upside down, I'll get a number that's smaller than 1. So I'm saying it's about there. Conveniently, my second one, I made turn at -1, so when you turn -1 upside down, you get -1. I think that's enough information now to draw our graph. Voila. So the red one is y equals 1 over function x. It's bending towards the asymptote, it's going through all our points, it's staying in those regions that I identified. Let me just get rid of the old one. There it is, but with a lovely point discontinuity at the x-axis. 5C is what we'll do.